Over the last week, we've mentioned a couple terms in the context of uniform circular motion. Frequency being the number of rotations per second measured in hertz, period being the time for one complete rotation or revolution, and then of course speed, which is just how fast the object is moving as we go around a circle. I'm going to focus on this one for a second. Do you guys remember why we talked about the speed of an object in uniform circular motion as opposed to the velocity of the object in uniform circular motion? Yep. Okay. Okay, well, you're on the right track partly, but then kind of went off a little bit there at the end. When you're going around a circle, um, you are going in a particular direction. In fact, at any given point, you're traveling at a tangent to that circle. So if we're looking at this point, your velocity would actually be in this direction. Okay, if you're looking at this point, your velocity would actually be in this direction. You're moving in a certain direction at any given time. There is a velocity associated with an object in uniform circular motion. But you can see just by the two velocities that I've drawn here, the velocity is always changing. So it's hard to describe this with velocity when the velocity is changing at every instant in time. But the speed isn't changing. In uniform circular motion, the speed is staying constant. That's what uniform means, right? Constant speed. Okay, constant speed going in a circle. So we talk about speed, not velocity. And we can find the value of the speed of an object undergoing uniform circular motion by using that equation that we learned here the other day. V is equal to 2 pi r over t, which comes from delta d over delta t. Really, it's a special form of that, but it's a special form that's unique to uniform circular motion. I want to talk about a couple more terms here today that you haven't seen before. One's called centripetal acceleration, and one's called centripetal force. Big word, right? Centripetal. The word centripetal means center seeking. So if we substitute that center seeking phrase in there for centripetal, then we've got a center seeking acceleration and a center seeking force. When we're talking about uniform circular motion, as we mentioned a second ago, the velocity is changing. Because the velocity is changing, there is an acceleration. Remember, acceleration was defined as the rate of change of velocity, not the rate of change of speed? Usually when we talk about acceleration, well, we're talking about the magnitude of the velocity, in other words, the speed changing, but it doesn't have to be. To have an acceleration, the velocity needs to change, and that can change by either speeding up or slowing down, or by changing direction. The speed isn't changing here. We're not speeding up or slowing down, but the direction is changing. And because the direction is changing, we have an acceleration. It's weird to think of that, right? You're going at a constant speed, but yet you're accelerating. Now you are because your direction is changing. That acceleration we call a centripetal acceleration. Centripetal again means center seeking. And you're going to see the significance of that in just a second. The centripetal acceleration is the acceleration experienced let's try to spell acceleration correctly here. The acceleration experienced by an object as the object moves in a circle. Where's the whole significance of the center seeking? Well, centripetal acceleration is directed toward the center of the circle. Well, that's weird. You got an object going in a circle. The speed's not changing. Okay, we understand, I think, that there's an acceleration, but the fact that the acceleration is directed toward the center of the circle, a center seeking or centripetal acceleration, that's weird. How can the acceleration be directed toward the center of the circle? When an object is going around in a circle like this, how can the acceleration, no matter where you are, how can it always be pointing toward the center of the circle? Well, let's talk about another term, centripetal force, and then we'll come back to how the acceleration can be directed toward the center of the circle. The centripetal force is the force experienced by an object as it moves in a circle. It's the force directed toward the center of the circle. This one's a bit easier to understand. Take a look up here and watch me swinging the keys around my head for a second. Okay, keys are not going in a straight line, right? They're going in a circle. They want to go in a straight line. They want to. They always want to, because every object always wants to go in a straight line until there's an unbalanced force acting, which keeps them from going in a straight line. Okay, these keys, if I let go of them right now, they would have hit Simon right in the head. They would have went off in a straight line. If I let go, you guys are all laughing. What if I let go of them right now? Then they would have hit Ashley right in the head. Why? Because they would go off in a straight line. In the absence of an unbalanced force, in the absence of a net force, they'll go off in a straight line. That's just inertia. Something has to be keeping them from going in a straight line right now. What is it exactly that's keeping them from going in a straight line? Well, it's a centripetal force because they're going in a circle. But what is it that causes that centripetal force? Remember that centripetal force in itself is not a fundamental force. It's always caused by something. Always caused by something. It's just sometimes we say it's a nickname for another force. Hey, the Earth going around the sun, gravity causes the Earth to go around the sun. Well, we changed the name of gravity to centripetal force because it's going pretty much in a circle. The electron orbits around the nucleus of an atom. Well, it's really an electric force, an electrostatic force, but we rename it the centripetal force and apply the equation mv squared over, or apply the equation that I'm about to teach you in a minute, because it's going in a circle. What is it that's causing the centripetal force when the keys are going around my head? My hand, right? My hand is pulling on the string, which is pulling on the keys. Where is my hand? In the middle of the circle. Okay, my hand is pulling on these keys, and my hand is in the middle of the circle. So clearly, the centripetal force must be pointing toward the center, right? And if the centripetal force is pointing toward the center, then the centripetal acceleration must point towards the center as well, because acceleration has to be in the same direction as the net force. Does that make a little bit of sense? Center-seeking acceleration, center-seeking force, the acceleration and the force that point toward the center of the circle. That's the force and the acceleration that keeps the object from going in a straight line. Now, let me give you a couple equations here. A couple brand new equations here. The first one for centripetal acceleration. Go ahead. Question? The question was, if there's an acceleration toward the center of the circle and a force toward the center of the circle, why doesn't that actually get closer to the center of the circle? Why does it maintain that orbit around? Let me create a new page for this so I can draw a picture here. Here's the middle of the circle, okay? You got an object that's going in a straight line like this, right? Which those keys at any given instant are going in a straight line, a velocity that's a tangent to the circle. So these keys are going toward the center of the circle. Well, what do we got? We got a force acting toward the center of the circle, right? The velocity is at a tangent, the force is toward the center of the circle. Where does the object end up going as a result of that force combined with its inertia? Go ahead. You're going to go somewhere in between there, right? Right. So now it's going this way, right? Well, wait a second. We got a force acting toward the center of the circle. So what happens? It ends up going this way, right? So what happens? Well, we get a force pointing toward the center of the circle, right? So now if you draw that on a much more microscopic scale with, not velocities at every 45 degrees, but velocities at every 0.1 degrees, then you would find the shape of the path ended up being, it would just keep going around in a circle like that. Does that make sense? Yep, right? All right, let's go through the equations for these two new terms, acceleration and centripetal force here. The centripetal acceleration, given by the symbol AC. It's a vector, so we put a little half arrow over it. But the equation that we're going to give you here doesn't tell us what the direction is. That's okay. We don't need to be told from an equation what the direction of centripetal acceleration is. We know already. What's the direction of centripetal acceleration? Always not a circle, toward the center of the circle, toward the center of the circle. So we don't need the equation to tell me that it's toward the center of the circle. The name centripetal acceleration tells me it's toward the center of the circle. That's a good thing because the equation doesn't tell me what the direction is. All right, centripetal acceleration is v squared over r. What does r stand for? Radius of the circle. What does v stand for? The speed, not the velocity, because the velocity is changing, remember. The speed is constant in uniform circular motion, and it's v. Sometimes we might have to find that using 2 pi r over t, and then plug it into here, and sometimes we might be given the value of the speed. What would the units be for centripetal acceleration? Yeah, it's meters per second squared. Look, v is meters per second, right? Meters per second squared over meters. Well, that looks kind of ugly, but if we could simplify that a little bit, meters squared per second squared over meters, cancel that out, and look at that. We're left with meters per second squared. Go figure. Centripetal acceleration has the same units as any other acceleration. Centripetal force, hey, how do you find the net force? Usually, mass times acceleration. So we're going to say the centripetal force is mass times the centripetal acceleration, which is, so let's say it's mv squared over r. Mass times acceleration, or mass times v squared over r. Units, of course, are going to be newtons. Mass is going to be measured in kilograms. These two equations are on your data sheet. All right. We talked a little bit about this already. Let me draw a picture, though, to illustrate this whole thing, this velocity. In fact, we'll illustrate velocity, acceleration, and the force here. Let's say we've got two different positions of the object. Let's say it's going counterclockwise. It doesn't really matter, but let's draw counterclockwise here. Let's say that green is going to represent velocity. Blue is going to represent acceleration, centripetal acceleration, that is, and red is going to represent the centripetal force. At this point, the velocity would be this way, tangent to the circle. At this point, the velocity would be this way, a tangent to the circle. If I was to, let's say, swing the keys around my head and let go at either of those 2 points, then the motion of the keys would be given by these green arrows, tangent to the circle. If I was to be going around a turn in my car and hit a patch of ice at this point, then I would go off in this straight line. Or if I was to hit a patch of ice right here, then I would go off in this straight line. That's the velocity. Now the acceleration, we said, is directed toward the center of the circle. So at those 2 points, the acceleration would be this way. The force is also called centripetal force, directed toward the center of the circle. So at those 2 points, the centripetal force would be pointing toward the center of the circle as well. So remember, centripetal acceleration or force toward the center, but the velocity at any given time is always a tangent to the circle, always going off in a straight line. We want to go green, but red keeps me from going green. Okay, red provides that unbalanced force, which takes us away from that straight line path. Okay, let's take a look at an example on page 255 here. DVD disc. We haven't seen DVD discs in a while now. We don't even use Blu-rays anymore. We download our movies now, right? But everybody knows what a DVD disc is, right? It's a diameter of 12 centimeters, and it spins around with a rotational period of 0.1 seconds. So it makes one complete rotation on its axis in 0.1 seconds. We want to know the centripetal acceleration at the outer edge of the disk. So in other words, if you got a speck of dust at the outer edge of the disk, what's the acceleration on that speck of dust? It's different than if that speck of dust is halfway out, right? The acceleration will be different because the radius is different then. What do we got here? We got a radius of what? 0.0600 meters. Right? That's the diameter. We got to divide that by 2, and then we got to divide it by 100. The period here, big T, is 0.100 seconds, and we want to find the centripetal acceleration. So we're going to say A is equal to V squared over R. That's my new equation for centripetal acceleration, but I don't know what V is, so I got to find that. Suggestion? 2 pi R over T. Good. So let's say 2 times pi times 0.0600 divided by 0.100 seconds. And what do we get for that? Let's see here. 2 times pi times 0.06 divided by 0.1 gives me 3.7699. Doesn't seem all that fast, right? 3.7 meters per second. It can walk almost that fast. It can run faster than that for sure. Let's square that and divide it by 0.1 seconds. Sorry, divide it by 0.06 meters. Gives me an acceleration Is that right? No, I forgot to square it. 3.7699 squared divided by 0.06 gives me a value of 237 meters per second squared. So, on your West Edmonton Mall assignment that you got this morning, based on our field trip yesterday, you have to find a number of times, you have to find the number of G's, okay, the G-force experience. And there's two ways to do that. One is to take the normal force, which is your apparent weight divided by the force of gravity. That'll give you the number of G's, apparent weight divided by gravity. Or the other way to do it is to take the acceleration and divide it by 9.81. So in this case, we take the acceleration divided by 9.81, 237, gives me about 24 G's. That would mean that a bug holding onto the outside of this DVD would have to supply a force that's 24 times the bug's weight in order to hold on. Otherwise, the bug would fly off in a straight line. 24 G's. Okay? The maximum G's you guys experienced yesterday at the amusement park was about 4. Okay? 4, for many of you, over a sustained period of 3 or 4 seconds going around that double loop was enough to make you start blacking out. Okay? Imagine 24 G's. Okay, you could not sustain 24 G's. Was there a question over here? Okay. Good there? Okay, I want you to work on a couple questions on page 255, 3 of them actually on page 255 at your desks for a few minutes, please. Let's do one more example, and then we will assign the rest for homework, and then we'll be done. Determine the magnitude of the centripetal force this time exerted by the rim of a dragster's wheel on a 45-kilogram tire. Tire has a radius of 0.480 and a speed of 30 meters per second. You can imagine how the centripetal force will be different if the speed is different, right? That's why if you've ever bought tires for your car, depending upon what kind of car you have and depending upon what you want to do with your car, you have to make a decision as to what rating of tires you get. Some tires are rated for higher speeds than others. Why is that the case? Well, because some tires can withstand a big centripetal force. Okay, if you have to have tires, if you're going at 100 kilometers per hour, your tires have to be a certain strength. The rubber in those tires has to hold the tires together with a certain centripetal force. But if you're going faster, then that centripetal force has to be bigger, so the tires have to be stronger, right? For lack of a better term. Okay, otherwise they'll fly apart when you're going 160 kilometers per hour, right? Sebastian? Yeah. Let's see what the force has to be for this one. Let's say FC is equal to mv squared over r. M is 45 kilograms. V is 30 meters per second. Don't forget to square that. Over r is 0.480 meters. So what do we get when we do this? Let's say 45 times 30. Don't forget to square it. Divide it by 0.480 gives me a force of 84,375 newtons, which is, to three significant digits, 8.44 times 10 to the 4 newtons. Now, if this tire is able to stay together when this much force is applied on it, then this tire will be fine. But if you go faster than this, you're going to require a bigger force to stay together, maybe 90,000, maybe 100,000 newtons to stay together. If the tire is designed to stay together for 85,000 newtons, then it may not stay together for 100,000 newtons, which is what you'd get if you were going faster than 30 meters per second. All right? We've got these two questions as well. So your homework tonight is the questions we have on page 255 that you were just working on, and the questions we have on page 256, please.